This section explains the transformer model and code implementation. Let's first look at the transformer model overview. The transformer architecture is based entirely on attention mechanisms, dispensing with the recurrent layers, like LSTMs and GRUs, used in traditional sequence-to-sequence models. The core of the transformer model consists of the encoder-decoder structure. The encoder processes the input sequence. The decoder generates the output sequence based on the encoder's representation and previous decoded tokens. However, in the context of language models, such as GPT, the transformer can also be used with only the encoder or decoder part. For this section, we'll focus on the encoder part of the transformer. Multi-head attention, the heart of the transformer. The multi-head attention mechanism is the key feature of the transformer model. It allows the model to focus on different parts of the input sequence simultaneously, rather than just one part at a time. This is achieved by creating multiple attention heads that operate in parallel. Let's begin by understanding the scaled dot product attention, which is the basic building block of multi-head attention. The formula for the attention mechanism is as follows. Query, key, and value are matrices derived from the input data. The scaling factor dk is the dimension of the query and key vectors, usually the same. K is the transpose of the K matrix to calculate the dot product. The softmax operation is applied to normalize the attention scores. The weighted sum of the values V is computed using the attention weights. The scaling factor is used to prevent the dot products from growing too large as the dimensionality of Q and K increases. Without scaling, the dot product can result in very large values, causing the softmax function to become too steep and making the gradients unstable. Multi-head attention improves the model by having multiple attention heads, each learning different aspects of the input sequence. The inputs Q, K, and V are split into multiple heads, and attention is computed independently in each head. The outputs of all heads are concatenated and pass through a linear layer to produce the final output. Query, key, and value projections as follows. The output from all heads is concatenated and passed through another linear layer as follows. H is the number of attention heads, and WO is the output projection matrix. The formula for multi-head attention is as follows. Positional encoding, handling sequence order. Transformers, unlike RNNs, don't inherently process data in order. This means they lack a built-in mechanism for understanding the position of tokens in a sequence. To address this, positional encoding is added to the input embeddings. The positional encoding is defined as follows. P is the position of the token in the sequence. I is the index of the dimension. D model is the model's dimensionality. The sine and cosine functions ensure that the positional encoding is unique for each position, but also similar for nearby positions. Each transformer encoder layer consists of two main sublayers. Multi-head attention, position-wise feed-forward network. The feed-forward network consists of two linear layers with a ReLU activation in between as follows. Final output. For tasks like language modeling or translation, the output is passed through a final linear layer followed by a softmax to predict the next token in the sequence. WF is the final weight matrix. BF is the final bias term. X is the output of the encoder or decoder. Now we implement the transformer code. Multi-head attention class. Positional encoding class. Transformer Encoder Layer class. Transformer class. Now start the test case. Testing individual components.